In this video, we're going to be talking about how do we calculate the volume of solids of revolution using something called the washer method. So this is essentially a follow-up to the previous lesson on disk method. So sometimes when you slice a solid, it creates disks, but other times it creates washers. So a washer is essentially a ring shape where there is a large radius and a smaller radius. So just to show you what I'm referring to there, almost if you picture a donut or a bagel, we have a circle with an outer ring, and then we have a circle with a inner ring. And basically for these, assuming these are concentric, they have the same center. You can see here that there is a large radius and there's also a small radius. So what we're going to be doing in these problems is trying to find the distance in here, which you could see is the difference between the big radius and the small radius. When we are calculating the volume of solids of revolution, the washer method is used when there is a gap between the region and the axis of revolution. So on the AP exam, for instance, they don't generally tell you to use disk method or washer method. You just have to know which method is more appropriate based on whether or not there's a gap between the region and the axis of revolution. So let's take a look at two graphs so we can examine the difference. So let's imagine that both of these regions are rotated continuously about the x-axis. You can see in graph A that the shaded region is just butted up against the x-axis. There is no gap. That would be a candidate for disk method. Whereas if we look at graph B, so here's our x-axis just to be clear here. And if I make this a little narrower even, you could see that there is an empty region in between. That's what's going to create that donut ring shape, or what we call a washer shape. So since we have to find the distance between the two radii, you can see that in our volume formulas for when there's a horizontal axis or a vertical axis of revolution, that we're going to be subtracting two radii. So this is essentially going to be like the big radius minus the small radius. And you can see each one of those is squared as well. It's going to be the same exact idea when we're doing a vertical axis of revolution, but everything is going to be in terms of y, including the bounds. All right, let's take a look at an example to practice this. So number 1 says the shaded region shown below is bounded by y equals 1/2 x squared, y equals 4.5, and x equals 0. Write, but do not solve, an integral that would express the volume of the solid formed when the region is rotated about the x-axis. So I'm going to draw in my picture here. So here's our x-axis. Let's draw in what the big radius would be. So that would be the distance from the line all the way to the axis. So that's big R. And then we should be able to see that from the curve, the parabola, to the x-axis, that would be our little r. So if we were able to do that and label that on the graph, we should be able to then go and set up our volume. So volume equals pi. Our bounds are going to be 0 and 3. And we're going to do the big radius squared. So that big radius is 4.5 minus 0 squared, minus the little radius, which is 1/2 x squared minus 0 squared, and then dx. Of course, can we clean this up and can we get rid of those minus zeros? Of course, but I'm just going to leave them in here to show how we were able to figure out the big radius and the little radius. So again, this represents our big radius. This represents our little radius. All right, let's try another. Number 2, it says the shaded region on the graph is bounded by f of x equals x minus 3 and the x-axis. Part A says write but do not solve an integral to express the volume of the solid formed when the region is rotated about y equals 1. So y equals 1, recall, is a horizontal line, so I'm just going to draw in y equals 1. And we're going to determine what the big radius is and what the little radius is. So the big radius is going to go from the line x minus 3 all the way up until we hit 1. The little radius is going to go from the x-axis up until 1. So I'm going to set that up, and I'm going to say that volume equals pi. We're going to go from 0 to 3. The big radius goes from x minus 3 to 1 squared minus the little radius, 0 minus 1 squared dx. Now, technically, if we had reversed this, so if, for instance, you had done, let's say right here, 1 minus 0, it will come out to the same answer mathematically because you are squaring it will give you a positive regardless. Now, for part B, I'm just going to erase what I have on the graph here, and I'm going to see that we're going to rotate this about x equals -1. So I'm going to go to my graph, and I'm going to draw that. And you can clearly see now we have a vertical axis of revolution. So the big radius is going to go from the line to that axis of revolution. The little radius is going from the y-axis to that axis of revolution. Now remember, this line that we were given was y equals x minus 3. If I get that in terms of y, meaning we get x by itself, we're going to get that x is equal to y plus 3, and we're going to need to use that when we set up our integral here. All right, so when we write our integral for b, v equals pi, we are going to evaluate this from -3 to 0. We're using the y values of that region. For the big radius, we're going to do right minus left. So y plus 3 minus -1 squared. For the little radius, right minus left. So 0 minus -1 squared, and then dy. For number 3, the shaded region on the graph is bounded by y, or f of x equals x cubed plus 2, x equals 0, x equals 2, and y equals 1. We're going to find the volume of the solid formed when the region is rotated about the x-axis. So our x-axis here, I'm just going to highlight the x-axis. And I'm going to label big R and little r in my picture. So big R is going to go from the cubic function all the way to the axis of revolution. Little r is going to go from the x-axis, or excuse me, from y equals 1 to the x-axis. And now we're going to set that up. So volume equals pi. Our bounds of the definite integral are the x values, so 0 and 2. For big radius, it's x cubed plus 2 minus 0, and then squared, minus, for the little radius, it was 1 minus 0 squared dx. Now, I've already gone ahead and I have plugged this in my calculator in order to evaluate this, and I got for my volume that it was 126.561. Okay, for our last question, number 4, the shaded region on the graph is bounded by f of x equals sine x and the x-axis, and we're going to be rotating this region about y equals -1. So I will be going to my graph, and I'm going to be marking off where y equals -1 is. And then I'm going to label big radius and little radius. So big radius goes from the sine curve all the way to the axis of revolution. Little radius goes from the axis, x-axis, and goes to the axis of revolution there. All right, so that being said, we have v equals pi. Our bounds are 0 to pi. Big radius is sine of x minus -1 squared. Little radius goes from 0 to -1 squared dx. And I've already, again, gone to my calculator, evaluated this, and calculated that the volume was 17.501.